Hey everyone, my name is Santiago Jimenez. I'm a Ph.D. candidate working with Ricardo Sanfelice at the Hybrid Systems Lab at UCSC, and we're going to present our paper on sufficient conditions and optimality for Finite-Horizon hybrid games. I'm going to talk about the intersection between game theory, control theory, and hybrid systems. Interesting scenarios arise under the presence of adversarial agents that may be designed to cause as much harm as possible. And this problem has been studied by employing game theoretical tools. Differential games return to the case when the constraints are given in terms of differential equations. So consider this quadruped robot and assume the control input is designed to accomplish a task in finite time under the presence of an adversarial action. We can model this scenario as an optimization problem with dynamic constraints. The challenges that arise in this system is that it exhibits both continuous and discrete behaviors, respectively, when the leg is flying and when in contact with the ground. In addition, the definition of a finite horizon in a hybrid time domain imposes additional challenges because it is almost impossible that if you fix a specific point in hybrid time, example 5 seconds and 5 steps, the robot will reach 5 steps in specifically 5 seconds. So we need to have a more general framework to denote what a finite horizon means. Mathematically, we model this by one player choosing the control action U1, aiming to minimize a cost J under hybrid dynamic constraints to accomplish a specific task. But we are interested in the case in which there is the worst case adversarial action that aims to maximize the cost function. And even in that case, by the player that selects U1 minimizing it, the task can still be accomplished. This type of formulation also applies not only to the case when input actions are selected by players, but also when there are two systems with hybrid dynamic behaviors. For example, a pursue evasion game in which the pursuer is allowed to bounce to target a flying vehicle. And this type of formulations find really limited resources in the current literature. So this will result in applying them will result in unsuccessful evasion maneuvers, which motivates the need to employ hybrid systems models to capture dynamic constraints associated to the non-smooth and instantaneous changes. To model hybrid dynamics, consider the case in which a state is allowed to evolve continuously via flow when it is found in a given set C, and it is allowed to evolve discretely when it is found in a given set D. And when these two sets intersect, trajectories potentially evolve hybridly in time. So we employ the framework by Gobel et al. So hybrid systems with state X are modeled based on a differential equation defined in terms of a flow map F when the state belongs to a flow set C, and a difference equation defined in terms of a jump map G when the state belongs to a jump set D. So solutions are parameterized by a pair T, G, where T is ordinary time, and J is a counter of jumps that have occurred. So the domain of the solution will be given in terms of union of pairs of intervals of continuous time and discrete elements. In this framework, we can model solutions that evolve in hybrid time. So the continuous evolution denotes increment on the ordinary time, and whenever a discrete event occurs, the discrete time will increase. We are interested in the case in which this system is modified by input. So the differential equation depends on an input UC, and the difference equation depends on an input UD, defining a hybrid system with inputs. This type of frameworks is convenient to cover different types of systems, as switched systems, impulsive systems, DAEs, and hybrid autonomous. And to the best of our knowledge, there does not exist a work that proposes a hybrid games formulation with dynamic constraints model with this general approach for Finite-Horizon scenarios. So consider a two-player game in which player P1 selects the input with subindex 1, and player P2 selects the input with subindex 2, each of them with a continuous and discrete element. And consider a cost function J associated to solutions to such a system from initial condition. The problem that we want to solve is this min-max problem of the cost function J, or the set of input actions with a terminal time in a set that we are to define calligraph T as a hybrid game. And this type of problems arise in many applications. For example, a robotics control problem, where you want to find a control input to upper bound the cost for a disturbance, or a security problem where you want to ensure the control input minimizes a cost under an attack decided to harm the system as much as possible. So we present a general framework to formulate this type of games, a result and conditions to evaluate the value function and the saddle point equilibrium, and an application in a security scenario. So to formulate this game, following the work by Bashar and Alter, we have that the each player has its own dynamics with its own data, its own state xi, its own hybrid input ui, and a set of hybrid inputs allowed to such a system. Remember that this formulation doesn't only cover the case in which systems need to have dynamics associated, but systems can be, or players can be reduced just to select a hybrid input. The elements of the whole game will be the joint state X, the joint inputs, the set of joint inputs U, in which each player selects its own action independently from the actions of the other players. The dynamics of the game in which the flow set is given by the product of the flow sets of the players, and the joint flow map F. And when any of the players triggers a jump, the joint dynamics trigger a jump as well. And this is captured by the joint jump set D and map J. The next element is the strategy space of the game K, that is a collection of mappings. Gamma is feedback loss, and the cost associated to each of the players K sub I. But we're interested in the case of analyzing when there is a single cost functional. So the player P1 has a cost that is minus the cost of player P2. And we have a special assumption here, and is that for every input action, we have a unique solution to the hybrid system, which also creates a unique correspondence of actions and cost functions. So our game is well defined, and it admits an equilibrium solution that I'm about to introduce. So we say that a feedback law gamma is a saddle point equilibrium if for each initial condition, every input action defined in terms of such a feedback law satisfies equation 1. So the cost when both of the players play the equilibrium strategy will be greater than when only player P1 selects the equilibrium strategy, and will be smaller than when only player P2 selects the equilibrium strategy. So this equation implies that no player has incentive to unilaterally change its own action, since it would lead to an improvement of its own cost. And notice that this is the way we describe solutions to the game in terms of strategies, but the solution to a hybrid system is a hybrid trajectory, a hybrid arc. Now we can recall in a formal way the problem is the main problem that we solve in this work by defining the cost associated to a solution to the hybrid system from an initial condition G with terminal time T, J. And this cost is composed by these three elements: the cost of flow that penalizes each interval of continuous evolution and adds the map, and the cost to jump penalizes each jump and adds the map. And we have a terminal cost Q. So the main problem can be recalled as the min-max problem over the set of input actions with terminal timing in the set calligraph T. When attaining such a optimal value in the function, we can define what is the value function of the game as J sub calligraph T star at a given initial condition. But how do we select the sub calligraph T? Well, basically, we need to be really careful because, as I mentioned before, we need to allow solutions not to be completely restricted. And the way we do it is by defining a window of time that is denoted by this box. So any solution whose hybrid time reaches such a box will be accounted as having reached the set calligraph T. We're ready to introduce our main results. So if we have a game with the elements that we just proposed, we want to study the following conditions that are given in terms of continuous evolution and discrete evolution. For continuous time, we are saying that minus the change of b over time is equal to solving this min-max problem in terms of the functional c and the change of b with respect to the state. Notice that in this case, the action u1 is selected by player p1 aiming to minimize this function, and player p2 selects action u2 aiming to maximize it. We say that the min-max problem is equal to the max-min, so we don't give any advantage to any player playing first. And just to build up a little bit intuition on what's going on here, we just want to drop the dependence on time. And if we take an optimizer as u star, we say that the cost of flowing is minus the change of b along continuous evolution, and this is what we are imposing with this equation. In the discrete version of it, at each interval of discrete evolution, we can say that we have our function b equal to the min-max problem, but now over the actions, the discrete actions, in terms of our functional d and v as well. And again, if we define our optimizer as u star, we can say that the cost of jumping by dropping the dependence on time is equal to minus the change of b along discrete evolution. So if we have this type of relationships enforced when playing optimally, recall that our cost function is defined in terms of function LC and LD, and by doing the corresponding substitutions, we can actually evaluate what is the cost when playing optimal, which is the value function. So we can evaluate the cost. And for more details, I want to refer you to the paper, but also to our previous publication on the CDC 2 years ago. Under an additional condition, when V is evaluated at the terminal time equaling the terminal cost, we can say that the value function is equal to such a function b that satisfies regularity conditions at the initial state and time. And any feedback law that is an optimizer of these min-max problems in continuous and discrete time is denoted as a pure strategy saddle point equilibrium for this hybrid game with a single cost. A quick application of this result with an actuated joystick system in which you have a ball where position is denoted by x1, velocity is denoted by x2, the dynamics of the ball when the ball is on the air are denoted by the differential equation, and whenever the ball is in contact with the platform, impact dynamics are denoted to modify the velocity, but we can inject energy to the ball by means of actions u1 that is selected by player p1 and action u2 selected to player p2. So what do we want to do? If there is a cost function j that player p1 wants to minimize, we want to study the case in which player p2 is playing the worst case scenario attack to maximize it under a Finite-Horizon calligraph T. So what will happen here is that trajectories will evolve hybridly, and whenever the ball is in contact with the platform, the player P2 is injecting the worst case attack, and we want to find what is the action the player P2 has to play so we can optimize the cost function even under the worst case attack. This will allow us to, by applying our results, evaluate what is our cost once it reaches the finite horizon, which can actually be predicted by evaluating the function p at the initial time. And the cost function for this case doesn't penalize evolution in continuous time. When it is discrete, it has a quadratic form, and the terminal cost has this structure that actually function b mimics to solve what we refer to as the hybrid Jacobi-Isaac hybrid PDEs. And based on our main result, if we evaluate such a function at the initial condition, that's how we can calculate our value function. And this is attained by the feedback law gamma D1 and gamma D2 that are the saddle point equilibrium. The bottom figure illustrates the saddle behavior by depicting the cost associated to each of the strategies played by each of the players. When player P1 selects the optimal strategy under the worst case scenario tag, which represents the saddle point equilibrium, the optimal cost is attained. Whenever the player P1 modifies its strategy unilaterally, that will only result in a greater cost in comparison to the optimal. Whenever the attacker decides to modify its strategy unilaterally, that will only result in a cost smaller than the optimal, which will benefit player P1. So for each of the players, the best action is to play the saddle point equilibrium, which is represented by the red dot. We presented a general framework to formulate hybrid games with finite horizon, and our main result with sufficient conditions for optimality to evaluate value function in terms of the Hamilton-Jacobi-Isaac hybrid PDEs with conditions to attain the saddle point equilibrium. And we presented an application in a security scenario. An extended version of this work portraying the case of Infinite-Horizon games can be found on the HSCC of this year. I want to thank our funding